since actually 2012, but became more active from 2015, encouraged by NBHM, which is National Board for Higher Mathematics. So IWM includes several activities. So let me say something about few of them. So one is like organizing short workshops in the different part of the countries. The goal is to reach out women who are involved in teaching or in research in mathematics, and especially the younger people who are intent to do research in mathematics. And second is other activities to have several talks by a prominent woman mathematician every year to lecture in a few places. And there IWM makes a point to do it in a smaller cities. This is for the purpose of presenting a role model. And then IWM also has an annual conference where active researchers present their work. So now, due to current travel restriction, most of these activities are taking place online. In fact, but the recent one was, I think, in a hybrid mode. Under this, we have visitors program lecture series, and this is the second session of the series. So in the first series, we had 5 lectures, and this is the first talk in this series, but it is by Professor Shihoko Ishii. So it is my pleasure to introduce her. She is a professor emeritus at the University of Tokyo and Tokyo Institute of Technology. So her area of research is algebraic geometry, and she's considered one of the leading experts in singularity theory. Her recent research interests include, say, things like arc spaces, jet schemes, multiplier ideas, etc. So she's the author of a graduate level book called, its title is Introduction to Singularities. So she has represented her country on several international forums. She has won numerous awards, which I won't list them, but I would like to mention here one of the early ones called Ishii Prize. So the reason I'm mentioning is as follows. What happens, these are awarded to a distinguished woman scientist in Japan every year. So in her interview in IWM, which is European Women in Mathematics, she mentioned that her role model is Professor Fumiko Yonezawa, a well-known physicist. And the first time she heard her name was as a Ishii Prize winner in a newspaper. And then she felt she very motivated, and it was so motivated to pursue further research. 11 years after that, she herself got Ishii Prize. So this is the story. Now I invite Professor Ishii to give the talk and later on share her experiences with us. Yeah, one more thing before, Pooja has reminded me that people should put off their, switch off their mic. So please, Professor Ishii.
Hello, my name is Shihoko Ishii. Thank you very much for the introduction. I'm very happy to meet you online. I'm going to talk about singularity on algebraic variety. Today, I will show you a small part of singularity theory with a little biased viewpoint. Please be sure that there are many other exciting problems in singularity theory. Okay, can I share the screen?
Yes, please go ahead.
Yeah. Okay. Can you see?
Yes. Can make it full screen?
Yes, it's the full screen. Is it too big?
No, it is okay. So I think.
Okay, okay. Sorry. Okay. Introduction to singularity. Please be sure that there are many other exciting topics in the singularity theory. The talk appearing in this talk is not covers whole singularity theory. Now, in this talk, I don't step into precise definition or explanation. Instead, I just would like you to feel the atmosphere of the singularity world. I have heard that the audience is mainly the undergraduate student. So the target of my talk is the undergraduate student. Okay, so shall we start? This is a program of my talk. In the first section, I will explain what is a singularity. In the second section, I will explain why we study singularity. In the third section, I will talk about the invariant of singularity. Invariant is reflecting some nature of singularity, and I focus on only 3 invariants of singularity. The fourth section, I will talk about future a little bit in my biased viewpoint. Okay. So in the first section, what is a singularity? Okay. A singularity appear in many fields in mathematics, but here singularity means a singularity on algebraic variety. Okay, thinking of algebraic variety. What is algebraic variety? Algebraic variety is the set of solution of finite number of polynomial equation. Okay, so set of solution. Okay, I will make a pointer. Okay, set of solution from x1 to xn. This is a combination of the number and the finite number of polynomial, say, like this, from f1, f2, to fr, are polynomial equation. Substitute this combination of number into each polynomial, then the value becomes 0. So we collect all these solutions and make a set. Then it is called algebraic variety. Okay. So we are thinking of n variable. So the subset algebraic variety is in the n-dimensional space with the coordinate. Okay. Yeah. Then I will show you the simplest example. Okay. Simplest example is the variable is two variable, and r equals 1. So the number of polynomial is only 1. And algebraic variety defined by an equation of this form, this one. Maybe you remember this inequality, this equality. Then you can imagine what does it mean. Okay, this is a circle on the plane, and all points on the circle is smooth. Smooth is in daily life sense, usual sense, not the terminology. It's an intuitive word. Okay. Then the next one is a rather complicated variety. N equals 3. So in the 3-dimensional space, we think of the algebraic variety defined by one polynomial equation. So the equation is very complicated, so please don't try to write down them. Okay, it's one equation, and the degree, the variable is x1, y, z, and the degree is 4, but the coefficient is rather complicated. This is because the picture becomes pretty. So it looks like this. So, okay, this appears in the first page of the talk. So the picture is like this. So you can see on this variety, most point here here, smooth. But this point are not smooth. These points are called singularities or singular point. Okay, so very intuitive definition. But here we skip the definition of singularity, a precise mathematical definition. We skip it. If you are interested in, please check textbook or article. But I would like to emphasize that mathematician can define such an intuitive terminology as smooth. Smooth is very intuitive. It is kind of feeling of a person. But the mathematician can define it in mathematical terminology. And because of them, it makes the people to consider an object which one cannot see physically. For example, singularity on a variety of dimension greater than 3. You cannot see it because we are living in a 3-dimensional space. So you cannot see the 4-dimensional or 5-dimensional variety. But still, we can see it in the mathematical world. So this is a mathematics advantage. We can see the invisible things physically. Okay, now, why we study singularities? There are at least 3 reasons. The first reason is in order to control them. The second reason is in order to make use of them. The third reason is singularities are interesting. Okay, so the first reason, control singularities. In early times in the history of algebraic variety, mathematicians tended to avoid singularities. Many research papers assumed smoothness on the variety that they are studying. Because without smoothness, many good properties of the variety fail. For example, Kodaira vanishing theorem, stability theorem, or cell duality and stability properties of varieties, and so on. Here, I don't explain the Kodaira vanishing or cell duality, but if you put them in the brain, and in the future, you can see it. Yeah. Just a keyword is deserved to memorize. Anyway, we should control singularity because the singularity violates good property. Okay, but we know that sometimes singularity do not violate good property. We should distinguish harmless singularity from harmful singularity. In order to control them, resolution of singularity is very useful. Okay, so how to do it? Sorry, I would like to organize the participant picture. It's hiding my part of my screen, so I'd like to. So it's maybe. Oh, it appeared. here. Okay. Okay. I would like to delete the people's picture. I'm sorry, because it's hiding part of my screen. Here, how to. Oh. Here, sorry. How to manage it. Okay, I give up.
Can I say, I think maybe there is something like a view on your screen. If you see, then if you click on that.
Yeah, people's window hide the part of my screen. So it's a little bit inconvenient.
Okay.
So
There is no cross on the top of it. Like cross that or pop in thing here.
Where is it?
Maybe if you, the participants, if you see at the bottom, there is participant and you click on that, then the name.
Okay.
Just click on that, participants, and then.
No, I cannot see the participant because I used the full screen mode of the slide. So, okay, it's okay. I will try without some part of the slide. Okay. Okay, shall we start again? And in order to control them, resolution of singularity is very useful. And what is a resolution of singularity? I will show you the simplest example of singularity. It is, okay, where is it? The castle. Where is the castle? Here. No, my cursor was lost. Maybe, please allow me to return the original one. Okay. So, yeah. So again. Okay. Then here. Okay, return and laser pointer. Okay, the singularity is here. Only one singular point here. Other points are all smooth. Okay, this algebraic variety is defined by this equation. Okay, so this point, focusing in this point, it looks like this. So this picture reminds us something in the real world. Yes, it's a intersection of two streets. If there is an intersection of street, the traffic is not smooth. If this car goes through this way, then this car should wait. So if you want to make the traffic to be smooth, then what do you do? So in the real world, there is a prototype. It's the three-dimensional junction. So we just mimic it. Pick up one street like this, then you obtain a smooth variety. So this procedure is called growing up at the singular point. And this is a resolution of singularity of one-dimensional variety. This is only one-dimensional case example, but there is a big theorem resolution theorem of singularities by Hironaka. The statement is like this. Every singularity on arbitrary dimensional variety can be resolved by some blowing ups. This is proved by Heisuke Hironaka in 1964. So it's a very big theorem. Okay, let me show you two-dimensional picture. Okay, consider the algebraic surface defined by this equation in three-dimensional space. Okay, then there is one singular point here. Then we blow up at this point. Two-dimensional case, we already saw the blow up, but one-dimensional case, we already saw the blow up. For two-dimensional case, blow up here, then we obtained two curves corresponding to one point, one singular point. And as a consequence, the variety becomes smooth. This is a resolution of singularity. Okay. So now you obtain a resolution of singularity, but if you pick up any point here, for example here, and blow up here again, then you obtain another point. Okay. And the new variety is again smooth. So this is also the resolution of singularity. So in this way, resolution of singularity is not unique. More than that, if you pick some point here and blow up here again, then you obtain another resolution of singularity. In this way, you have infinitely many resolutions of singularity. So the important point is that at least one resolution of singularity should exist. Okay, so Hironaka proved it for arbitrary dimension. So it is very, very useful, but we should be careful. In Hironaka's theorem, variety should be defined on a field of characteristic zero. This means that we consider the solution. It's a combination of numbers, but these numbers are element of a field of characteristic zero. This is a very important assumption for Hironaka's theorem. The resolution theorem does not yet prove in general for positive characteristic case, so you should be careful. But still, even only for characteristic zero case, the resolution theorem works very well in to control singularities for varieties in characteristic zero. Many discussions for singular varieties are reduced to the discussion for smooth variety. Because of this, singularities theory developed dramatically. Many concepts of singularity appears by making use of resolution theorem. Here, I show some names of singularity, but please do not be nervous at the unknown word. I just would like to emphasize that each singularity appeared from different background. Still, they have interesting relation each other. Okay, the first line, rational singularity, rational double point, elliptic singularities, This singularity came up by focusing difference of homologies between original variety and resolved variety. Okay. The second examples, terminal singularity, canonical singularity, and log terminal singularity. It will appear in the next slide. This singularity appeared in birational geometry. Birational geometry is to study what happened by blowing up and blowing down. This is a description, of very roughly speaking. Okay, so the third one is a singularity. Dubois singularity appears in Hodge theory. In the quotient singularity, cyclic quotient singularity, these appears as a quotient of smooth variety by some group action. So there are so many rich concepts in singularities world, and these are somehow harmless singularities. And in some sense, these are well controlled. Okay, for example, one obtains Kawamata-Fiebeck vanishing theorem. This is a generalization of Kodaira vanishing theorem. I told you that Kodaira vanishing theorem does not hold for singular varieties, but it holds for varieties with only mild singularity. Here, mild means log terminal singularities. Okay, if the variety contains only log terminal singularity, then the Kodaira vanishing theorem also holds. So, in this sense, somehow singularity is controlled. The second reason is make use of singularity. Okay, I will show you one example. Up to two-dimensional case, every variety has smooth minimal model. Okay, here I explain minimal model. But before going to the definition, I will show some negative statement. But for higher dimensional case, there is no such model in general. There is no smooth minimal model in general. Sometimes yes, but generally not. Okay, so I will explain minimal model. We say minimal, but minimal in which sense? Minimal in which order? Yeah, the order is defined like this. This is the same example which appears before. There is a smooth surface, okay? And blow up here and you obtain the new smooth surface, okay? Then we define this surface is bigger than this, okay? Because this variety has extra curve. In this way, by blowing up this, you obtain more and more bigger surface. But you can think that the smaller surface is better because comparing these two surfaces, this surface contains an, how to say, unnecessary curve. Yeah, so maybe this is better than this. This is a usual sense, and I think it's correct. And minimal is better. So we would like to minimal. It means economic and smooth variety. Yeah, we want that. And two-dimensional case, it's possible. Yeah, but higher dimensional case, it's not possible. So here, we stick to the smooth case. The minimal one should be smooth, but we give up the smoothness and allowing mild singularity. There is a hope to have minimal model in general for higher dimensional case too. Okay. So actually for three-dimensional case, there is a minimal model with mild singularities. Yes, this is proved by Shigefumi Mori, and he was awarded Fields Medal. And for higher dimensional case, greater than or equal to four-dimensional case, general variety have minimal model. Here, general means not usual sense. In usual sense, general variety means all variety, but this is a terminology. There is a definition of general variety. So it's not all variety, but general variety is quite general. So the comparing with other varieties, the amount of general variety is bigger. Yeah. So it's a both. This is also a very big theorem. And Bilka, it was proved by Bilka and three other people. And Bilka was awarded Fields Medal. So this is a successful example of making use of singularity. So allowing mild singularity, we have a beautiful structure theorem. Okay. So this is only one example, but we can expect more successful example by allowing mild singularities. And the third reason is singularities are interesting. There are many surprising relations with other concepts in singularities. So there are many examples of showing interesting of singularity. But here I show only one example, and in the next section, we will see such an example. Okay. Okay, so the third section, invariant of singularities. Okay. There are many invariant represent nature of singularities. Here, I focus on three invariant. The first one is number of essential divisor. The second one is number of Nash component. The third one is minimal log discrepancy. So I will explain them. Any question? Okay. The first, I will tell you the problem which first two invariant appears. This is Nash problem. It is post 1968. The statement is like this. For every singularity, the number of Nash components coincide with the number of essential divisors. Okay. So we should explain both concepts, Nash component and essential divisor. Okay. What is an essential divisor? Again, we pick up the friendly example. This appears in several times. At a singular point, we blow up and obtain a resolution. Okay, and blow up here again and obtain another resolution. Here, the two black curves are called essential divisors. And the red one is called non-essential divisor. If you pick up any other point here and blow up here, and you obtain the new curve, this new curve is again a non-essential curve. In this way, non-essential curves is infinite. But essential divisor is, in this case, only 2. So essential divisor is always finite for any singularity. So this is definition of essential divisor. Of course, how to say, not precise definition. Okay. Then what is the Nash component? This is a counterpart. In order to define the Nash component, we should give the notion of arc. Let X be an algebraic variety of our field K. P is a point on K. An arc with center at P is a K-morphism from spec K from our power series ring to X. Okay, here we should say more precisely an arc of X with center at P. This is a more exact statement. This is a more K-morphism from this scheme to X. And this is formal power series ring, and dimension is 1. So you can imagine that this is a kind of curves, but very, very small portion of curve, because as a topological space, this is consisting of only 2 points, closed point and generic point. Here is the term with center at P means the closed point of spec KT goes to the specified point P. This is the meaning of with center at P. Okay, so an arc with center at P with a cross point going to P. Okay, so we think of the set of all arcs with the center at P. This set has a scheme structure. Okay, scheme is a generalization of variety. Variety is, you remember, that defined in the n-dimensional space. So, of course, the variety is finite dimension. But the scheme is a generalization of variety, and the dimension is not necessarily finite. So actually, for usual X, so the dimension is better than 1, then this scheme the set of arc with the center at P becomes infinite dimension. We denote this scheme by this, this symbol. P is a specified point. And infinity implies a arc. We are thinking of arc on X. Okay. So this is usually infinite dimensional scheme. Okay. So this is infinite dimensional scheme, but this has only finite number of irreducible components. This component is called a Nash component. Okay, so totally different word from resolution of singularity. But it's a space of small portion of curves. Small portion of curves. The irreducible component is Nash component. So quite different word. So the Nash program said that this Nash component, number of Nash component, and the essential divisor, which I show as black curves coincide. Okay, note that if P is smooth, then the Nash component is only one. But if P is singular, then the number of Nash component can be more. Of course, sometimes it becomes one, but it can be more than one. And we think that this number represents a nature of the singularity. Okay, so let me show you a very intuitive picture of arc. Arc is, as I told you, the small portion of curve on X. So consisting of only 2 points, cross point and the generic point. So it looks like a tadpole. Cross point is a head and the generic point is tail. Okay, this looks like this. So since it's a morphism, send this tadpole to here, then this attached to, sorry, it's here. Head is here, okay? Anyway, this tadpole is on the variety. And each Nash component is the set of arcs. So it's a kind of family of arcs. So this is a member of the Nash component. Then maybe if it's a smooth point, then it's attached to here. Oh, sorry. Okay. So the center is at 1 point. So the tadpole's head is concentrated at the 1 point, but my skill of drawing the picture is very bad. So the heads are diverse, sorry. So the head should be concentrated 1 point, okay? Okay. Next, if P is singular, then the number of Nash components can be more than one. So if P is this point, singular point, then the one Nash component attached here, the member of Nash component attached here. Then other Nash component has family. This family is attached here. Sorry. Yeah. So Nash problem predicts a relation between two totally different concepts. So how he reached to this idea? He thought the following correspondence. Take a resolution of singularity. This is given. This singular variety is given, and take a resolution. Then one Nash component corresponds to a family of arcs like this. So pull back by this resolution of singularity, and it attached to this. So this singular point correspond to this and this and this. So one family is pulled back in this way, and the other family is pulled back to the other essential divisor here. Okay. The head is on the line. The head is on the line. Okay. Now, corresponding is like this. So I will show the history of the Nash problem. This is post 1968, and 2004 affirmative answer for arbitrary dimensional toric varieties are given. And in the same paper, negative answer for non-toric variety of dimension greater than 4 is given. Next, 2012, affirmative answer for two-dimensional case is given by making use of topology. The fourth, the negative answer for three-dimensional case is given.
Sorry, Professor.
Okay. So the first, one and two are proved by Ishii and Kola, and 3 is proved by Bobadilla and Pereira, and 4 is by Dufresne. Okay, so you can see that the affirmative answer is only this and only two-dimensional case and the toric case. Okay, but there are some negative case. So you can see that Nash problem is very delicate. Sometimes the answer is yes, and sometimes the answer is no. So, but it does not mean that the problem is stupid. The problem plays a very important, this is not necessary, important role. It became a bridge between birational geometry and the space of arc. As I told you before, birational geometry is a study of what happened by blowing up and blowing down, and the space of arcs, quite different things, but Nash problem built the bridge between them. So one of the successful product of this bridge is the description of invariant of singularities appearing in birational geometry by means of the space of arc. This is a very successful product. And minimal, the invariant is minimal log discrepancy. This is an unexpected relation. Let me show you the formula. X is a defined variety defined by equation. F equals 0. For simplicity, I write only one equation. Okay. Then P is a point. Then the formula is that MLD, this is a minimal log discrepancy of X at P. This is a birational invariant. This is the infimum of M. M is any number of N. N is a natural number. N minus 1 is a dimension of X. So dimension, this one is mysterious. Okay, I will explain. So this is the invariant of birational geometry. And this is a space of M truncated arcs of X. What is this? You remember that arc is a morphism from spec K formal power series ring. This part is different. Formal power series ring to X. This was the arc, but here we truncate formal power series ring at degree n plus 1. Okay, we think of these truncated arcs for M. Then the space of such truncated arc becomes again the scheme, but it's finite dimension. It's a difference of arc space. So this becomes finite dimension. So it makes sense to define the dimension. Okay. So you can see the definition. Okay. Anyway, MLD is an invariant of birational geometry, and this is computed by a divisor obtained by appropriate blowing ups of X. So for computing this value, you should make a blowing up several times. But for this is a space of arcs or a space of truncated arcs. So it's already there. And if you are given variety X, then the arc space or truncated arc space are already there. You need not to make any procedure. So this inequality shows such a different things coincide. So it's very useful. And one of the advantage of this formula is it holds also for positive characteristic. That formula is proved by Mucci-Mustaza under more general setting in characteristic 0. And Anna Legera and I proved such more general setting theorem in characteristic positive. So this minimal log discrepancy is very useful for minimal model problem. So we expect that for positive dimensional minimal model problem can be proved by making use of this formula. Okay. Let me say something about the future. So, minimal model problem is not yet proved in positive characteristic. It should be challenged. The relation among invariant multiplicity, I didn't mention about this. Embedding dimension, this also I didn't mention. MLD, this is a minimal log discrepancy. There are many, many invariant. These invariant relations should be clarified. And resolution theorem for positive characteristic also should be proved. There are still many, many people who are challenging this, but still it's not proved completely. Okay, the most interesting problem for me personally is DGK decomposition. Greenberg-Greenberg-Kazan decomposition. So let X be an algebraic variety over the complex number field. Let X infinity the space of arc of X. In the last slide, we specify a special point X, P of X, but we think of all such center. So this becomes arc space for any center with any center at X. So this space becomes much bigger than X infinity bracket P. Okay. Now take any alpha. This is an arc. Then there exists a variety. It is, of course, finite dimension. X infinity is infinite dimension, but Y is finite dimension. And such that X infinity is Y times C infinity in the neighborhood of alpha. So it's surprising, yeah, surprising result. So I think it's natural to consider what is the relation of the singularities of X and Y. I think it's a natural question. There should be any relation between them. Some examples are observed, but at this moment, we cannot find any clear relationship. We should challenge. There are many exciting problems waiting for your challenge. Thank you for your attention. This is the end of my talk. Thank you very much for listening.
Thank you, Professor Ishii, for giving such a nice talk, especially trying to express all these technical results in a simpler form for the non-experts. So, are there any questions?
Okay, I think Professor Shihoko.
Yes.
Thank you very much for your brilliant talk.
You're welcome.
You have explained so many brilliant results.
Thank you.
In a very short time. And thank you very much. And regarding that, initially you have discussed a lot of problem with the suppose field of varieties over field of characteristic 0. I think there might be problem if the characteristic is greater than 0.
Sorry.
Yes. You have proved, you have discussed a lot of result with over the field of characteristic 0. But if we consider the field of characteristic greater than 0,
Uh-huh.
then I think some of the results, I think very difficult to prove.
Ah, yes, yes, yeah. For example, you mean the Nash problem?
Exactly, yes, right?
Yeah, yeah. In that case, yeah, very difficult. I think so, because the resolution theorem is not yet proved. Yeah.
And you have discussed the singularity, and there are isolated singularity and non-isolated singularity.
Ah, yeah, we treat the non-isolated singularity, but in my talk, for the simplicity, I assume that the singularity are all isolated, because we are, my research is not only isolated singularity. So the people, research is not only isolated. So, yeah. By my talk, you may think that I treat only isolated singularity, but no. Sorry, I maybe too simplified.
Okay, that's fine. And some of the figures seems to be related with the fractal geometry. Some of the your figures, that means surface of this, seems to be a figure in fractal geometry. Fractal geometry.
You may think that.
I think whether all these singularity or resolution of singularity are related to the fractal geometry, picture of fractal geometry in nature, that is also quite interesting geometry.
Sorry, I don't catch the meaning of your question.
Okay, anyway, thank you. Anyway, thank you very much for your nice talk and brilliant delivery presentation. Okay, thank you very much.
Yeah. So sorry, I escaped this. I escaped this. Okay. So is it okay?
Okay, that's fine. It's okay.
I appear, some comment appears on my screen, so I try to finish it. Is it okay?
Okay, okay, right.
Mm-hmm. Any other question?
There is somebody has put something on that. Okay. It's the same person. Is there any link?
There is a question.
The same person,
any link with fractal geometry? Yeah. So yeah, I think in a deep place it may have some relation, but at this moment we cannot see directly. Yeah, this is the future's task. Yeah. Professor Talin Kumar Dutta.
Recently, I wrote to you. I think you are remembering my name.
Yeah, yeah. Thank you.
Okay, okay. I'll contact you again. Okay, right.
Mm-hmm.
So, are there any other questions? There are quite a few algebraic geometers here. So, the Parmo is there, Srinivas or something. So, yeah. Parmo, you singularity person.
Yeah. Anyway, thanks for calling me, but no, I don't really have a question on this.
Yeah.
Yeah, thanks.
Hello,
It was a nice talk.
Hello.
I really enjoyed your talk.
You have read?
Yes, I'm afraid these days with Corona, one can't go often to the barber.
Oh, it's surprising. And do you see that I let my hair cut?
Well, in Japan, things work differently, I think.
Yeah.
I enjoyed your talk very much.
Yeah, thank you very much.
Thank you very much.
Yeah, I didn't expect that expert appears in the talk.
No. I mean, in this
It's
topic,
only
you're the
for
expert. We are there to learn.
you. I thought everyone is undergraduate student.
Yeah. So Ishii, this Nash problem is for any characteristic it was posed?
No. Toric case. Toric result is any characteristic.
Yeah, right. But
Yeah.
two-dimensional, you said two-dimensional.
Yeah, two-dimension, no. He used, no. He used, Bobadilla used the topology. And I don't think so.
Right. It's a Bobadilla's with his student, right? Bobadilla with one of his student, one lady. They use pure topology. Yeah.
Yes.
But they also had the dimension restriction, right? I thought they were mainly on dimension 3 or something.
Dimension 3?
They were not done for high dimensions, no?
Yeah, the Bobadilla's result is only for 2 dimension.
Right, dimension 2,
Yeah. The discussion does not work for higher dimension.
Right.
Do we know it's false in dimension 2 in positive characteristic? We don't know, right?
I don't know.
Not that time.
I don't know.
It's a good problem for somebody to try.
But it's very difficult.
There's also a different notion of arc in positive characteristic, right? There are two kinds of notions. I mean, aren't there things like divided power arcs of some kind? Instead of using the power series ring, use some kind of divided powers. Because you're on positive characteristic, it produces another kind of arc space, I guess, a priori. I don't know. Well, anyway, it's a thought.
So Ishii, there are other questions. Somebody.
Yes.
Yeah.
Can we find some interesting results in strong desingularization? Strong desingularization, what does it mean? So it's an embedded resolution? Who asking this?
Yes, it's the same person, Taruni Kumar Datta.
I think this is from Sridevi. Probably Sridevi must have taken.
I don't know a strong desingularization means, but the people knows log resolution. We sometimes use log resolution, and the log resolution is quite strong. So if you are given some ideal on a given variety, then by the blowing up, then you obtain a smooth variety. It is not only smooth, but also the fiber of this ideal is also simple normal crossing. This is, I know, the strong result of resolution. So I'm not sure you mean this singularization. Sorry. The next one is there a construction of resolution of singularity, at least in small dimension? There are many research to construct algorithm, good algorithm to make a resolution of singularity. Yeah, I think so. There are many researchers doing it. Yeah. So, for example, in Germany, the Anna Frubis-Kuga is working on this reaction. Is it okay?
I don't know the person is responding or no. So, Sri Devi. Yeah, Sri Devi, you are saying something? We can't hear you. So we can't hear this person actually. Yeah. So are there any other questions? Professor Gurjar is there. So, I don't know whether he can hear actually. I have been trying to catch his attention. He's not. Hello, Professor Gurjar. Anyway, so
Gurjar can't speak. He has no speaker.
what is that? I don't know. He's not. Perhaps he can't hear. I don't know what is happening here.
I think his audio is not connected.
Right. He has no speaker.
Yeah. So are there any question?
Can I ask one question? I'm just curious about, so you said this minimal model problem that's not solved for positive characteristics. So that's not in any dimension, not even like
In smaller dimension, there are some result. For example, two-dimensional case, there is a result, and a part of three-dimensional case is solved.
in there exist? I mean, the answer is that yes, there are.
Exists, positive. Non-exist, not a non-existence, so exists.
So Ishii, you're saying this Nash components can be infinite dimensional.
You mean the
those arc spaces?
Positive characteristic case?
No, in any characteristic, it can be of infinite dimension, you're saying.
Finite dimension.
Infinite dimension.
Infinite dimension. Yeah, it's possible. Infinite dimension. You mean the variety is finite dimension, or the
this arc spaces you connected,
space
right?
Is finite dimension.
Yeah.
Yeah. This is possible.
Okay.
But I'm afraid it's interesting or not. May not be interesting. So, but I see. You were the person of arching ring. You interested in arching ring?
Mm-hmm.
Yeah. It may be possible. So that direction I didn't think, but it may be interesting. Yeah. I didn't think that. Yeah.
Okay, so are there other mathematical questions, or I think there are no other questions. So you want to ask some other question, non-mathematical ones? Pooja?
Yeah, Professor, can you tell us like how your journey was so far? Like how did you come to, I mean, I think Vijayalakshmi mentioned you saw some news in the newspaper and then you kind of, but how was it in the beginning for you? Like, and how has been your journey so far? If you can tell us about.
You mean the journey in mathematics?
Mathematics, yeah.
Yeah. When I was an elementary school girl, I was not good at mathematics because mathematics is a calculation. I was very slow to calculate. So the teacher thought that I am very bad student. in the middle school or high school, the percentage of calculation is less and less, then I like to do mathematics. Yeah, I like to think. I don't like calculate. So now I'm very happy because I can think of mathematics.
I think we in our school we had something that you had to compute interest and compounded interest, that kind of mathematics, and it was very intimidating. It was scary, like so. It becomes abstract later on, I think. So you said you come from a rural side of Japan or something?
Excuse me?
You said you initially you were belong to a rural part of Japan. So
yes. Not the Tokyo, rural part. Yeah, it's face to Japan Sea. So it's face to the how to say, Russia and China, not the Pacific Ocean.
Okay. But were there other women who were in mathematics? Who are your time? Were there other women mathematicians during your, means when you were growing up, when you're doing research?
No, unfortunately, no, because the people thought that mathematics is a job for men.
But in university, for example, when you were doing research, so were there other women at all, or?
Yeah, it was. It depends on the university. The Tokyo Institute of Technology, there was only 2 or 3 women professor or associate professor or assistant. And in University of Tokyo, there are 3. And nowadays, they try to hire more and more female mathematicians. And now I think there are 5 or something like that. So
5?
5, I think so.
But that's a very low number.
yes, because the number of faculty in University of Tokyo, the mathematicians are 60.
Okay, so not so bad.
Among 60, the 5 is a very, very small number. Yeah. How about in your university?
University, Padmavati, you have something to say?
I think we have a good number of women in our school. We have a good number of women faculty in our school.
Can you, Padmavati, can you open your video? Something?
I wanted to ask whether in Japan, do you have any programs for women, to encourage women to take up mathematics or science like we are trying to have in India? Because I think Japanese are also very, traditional like the Indians, and probably the women might have faced similar issues in Japan, in terms of taking up research and, going for higher studies and all that. So how is it now in Japan? What is the situation like?
You mean the number of female studying mathematics?
Mathematics, science, anything?
Science?
Yeah, in particular mathematics.
In particular.
So she's asking, do you have any program to encourage women? To get to start doing research in mathematics.
Yeah. There exists. The people are trying to encourage girls to take the course of mathematics or science, but it's not so successful. Maybe It's very difficult. It's
But
the culture, Japanese culture is very biased. So the people believe that science, mathematics are for men. So we try to convince them it is wrong.
Did you have a role model to
Yes.
take up research in mathematics?
Yeah. In former time, when I was a student, elementary school student or junior high school student, there was no role model, female scientist, but only role model for me was Marie Curie. So it is, she is too far, and so we need a very, how to say, very friendly and very close to role model. So for me, the physicist, the female physicist, Fumiko, you, Trivedi-san said.
yeah,
Fumiko
Yonezawa, you said.
Yonezawa. Sorry, I forgot. Fumiko Yonezawa. Yonezawa was the role model when I was a graduate student. Yeah. She was very attractive, and she married, and she had 2 or 3 children, and her achievement is very great, and she took care of the physics, Japan Physics Academy. She's a very powerful person. Yeah. Anyway, we need a role model. Not so far. Close to myself. We need it.
In your personal life, did you face any problem just because you were continuing research in mathematics? Was there any moment in your life where most of the women come to a place where they are, at least in India, they are deciding whether to continue with a career in research or to settle in the family and all? So was it like a issue for you at any time?
Yeah. When I get the first permanent job, just before getting the permanent job, I was always sway this way and this way. Quit the job, quit mathematics, or continue mathematics. I always sway the both direction. And my husband encouraged me very much. He told me that, if you want to quit, you can do it anytime. So anyway, continue. Then you can quit anytime. So you should continue. And he tried to convince me that you are the person who will make a good job. So he encouraged me in this way. Yeah. So without him, I cannot continue mathematics. Yeah.
But if you quit once, it's very hard to join back.
Yeah.
It's not like a bank job or something.
Yeah.
I can come back to mathematics. This is a problem.
Yeah.
But here we do have some programs of the government where women can come back and take up research, like we have in the Department of Science and Technology programs.
Yeah.
Right?
But it's harder to, in theory, you can come back.
The quality cannot be, it will be compromised for a while at least. And even age, right? Even age restrictions make us even more difficult to get a job later if you wish to, right? And all those things are there. So if you're taking a break at that time, it's kind of very... So do you have also age restrictions regarding job and all in Japan? I would like to just know. I mean, so in India, you can get a permanent job only if you are 35, I think, or 35 or below, the first assistant professor job and so on. So are there such restrictions, age restrictions there also in Japan regarding jobs when it comes to that?
Yeah, I don't know the point of your question, that maybe I misunderstood it.
So let me clarify. So in India, if a woman wants to take a break and then come back, so suppose before the first job, they took a break for a couple of years, then usually their productivity reduces. Suppose at that time she gave a birth to a baby. Productivity reduces. It takes a couple of years before she can show her publications again. But then that delays, that means that she sometimes gets more than 35, and then getting a permanent job becomes difficult for her in India. So I'm wondering whether such situations are there in Japan as well. I mean, are there issues there?
Yes. For women, the most difficult part is to get the first job. Then if you get the first permanent job, then even if you have a break as a maternity or how to say the associating work, 2 or 3 years, and it's easy to come back. But if you don't get the permanent job, then it's difficult to get the permanent job at first. So, how to say, to encourage to get the permanent job and having a child birth, there is a system of JSPS, and the system is like this. If the person who don't know the permanent job and pregnant, then she needs 2 or 3 years. Then during these years, the JSPS pay, or try when he returned. This is one case, and also when she returned to the job after the birth, then the JSPS pay for some years until she get the permanent job.
This is like something like a fellowship that
it's a fellowship. It's a fellowship. Yeah. So maybe I don't answer your question because it's very difficult to listen in the remote, and the Indian pronunciation is very difficult for me. Sorry.
No, I think my question was well answered. I just wanted to know how it is there compared to India.
Yeah. I also would like to ask the Indian situation, but how many women mathematicians in India? So you mean just a percentage?
Oh, I don't know. Pooja, I don't know. Pooja, do you know? Or
I think Geeta could answer this question better.
It changes, but from university to university.
Yes, I know. But there is no total statistic.
Oh no, there is. I'm sure. It's a pretty low, but the number is actually pretty low.
8-9% would be kind of average out over universities and institutes.
So it is like suppose if you are in a theoretical science, like physics or mathematics, number is certainly very low at the research level. I mean, after that, if you are in experimental sciences, in physics is still, at least here it is low, but in biology there are quite many more women than men.
Yes. This is the same as in Japan.
Yeah.
Yeah.
But here it is pretty low in theoretical sciences. So like always we get flack from review committee.
Mhm.
We should have more women, and there aren't any. I mean, at least like Pooja was in IASC, and she was the only one woman there. I think single woman.
Oh.
At some
Oh.
point, now there
Yeah,
are
but then now there are three, right?
now two. I mean, I have left, so two.
Yeah, so that is a cheating because TFR we were two, and the TFR person has gone there. So I am the only one in my institute right now. So in mathematics, I am the only one. And then if I look at in the corridor, which is physics, theory of physics, there are no women. And the other thing was since last so many years, we didn't have any women students also in the TIFR. So this has like happening like more since 4 or 5 years. There are no women students. Yeah.
Professor Ishii, may I ask a question?
Sure.
When is English taught in Japan? I thought even research is done in Japanese, and there are journals in Japanese where the researchers publish. So is English taught in school, or is it learned after you finish your high school?
Yeah, we finished the high school, then usually the student go to the university. And what is your question?
My question is when is English taught in Japan?
So when
I mean, do you learn it?
Ishii, she's asking when the children start learning English in Japan.
I see. Yeah, in junior high school.
Did you learn to do mathematics in Japanese or English in school?
Yeah. In Japanese, yeah. Children start to learn English in 12 years old. And the mathematics, they learn mathematics in 6 years old. So the teaching mathematics is done by Japanese.
So when do you learn to do mathematics in English?
Mathematics, not learn mathematics in English. Maybe it's in graduate school or final year of undergraduate. So at the seminar, we should read the English paper or English book, and we should present in front of the blackboard. This is the first time to learn mathematical English.
Is that very difficult transition?
Mathematics, no.
No, English, in English.
English in mathematics is not difficult. But talking English or to say chattering English in the conversation is difficult for Japanese because the construction of language is completely different and the structure is different and the pronunciation is also different. And the most problem for Japanese to learn English is the mentality of Japanese people. The Japanese people is shy. They are afraid of making mistakes. So it's difficult to learn English because by making a mistake, they learn many things. But for Japanese people's mentality, it's difficult to make a mistake.
Yeah, so if you teach a language from a very early stage, then you pick up faster because you're not afraid of making mistakes. Small children, they pick up language much faster because they are not scared to make mistakes.
Right.
Always this.
Actually, in small children, it's not yet Japanese fever.
Okay.
According to growing, then the children become Japanese.
According to some studies, if you learn in your mother tongue, then you learn better. That is what I read somewhere, but I don't know. I said that probably it is better to learn in your mother tongue first and then learn, to do it in English. Probably, I don't know. In many countries it is done. In Germany and Russia, I think they learn mathematics in their own language first.
So you suggest the order of learning English or mathematics? No? Sorry.
I don't know. I'm just telling you about something that I have read somewhere, that it is probably better to learn in your mother tongue first, and then pick up whatever you need to know later, like English, for example. Many students in our university have studied in their mother tongue, mathematics in their mother tongue. And after joining the university, they learn to, speak English and do mathematics in English. And they do very well, actually, some of them.
Yeah, but in India, most people in a school speaks English,
Yes,
even in elementary school, because the Indian people speaks English very well.
Yeah, that is correct. But nowadays
Not
it is
everywhere.
almost true. But like, for example, I studied in my mother tongue, and after 10th standard, we started everything in English. So same, Puja, it's same for you?
I studied in Punjabi till 10th, and then everything was switched. So but those 2 years were very difficult because I studied like science in Punjabi, and then I had no knowledge of what is velocity, what is momentum.
Yeah, right. I remember I did well in 10th, but my 11th and 12th were very bad, actually. I thought I don't know anything as a. It is difficult, yeah.
So yeah, it's difficult to know what time switch is good.
Somebody has,
I wanted to ask one more question. This is like a question that we usually ask all our speakers. So what would you give an advice, like looking back now, your journey, what would you give an advice to younger generation of women mathematicians? Yes.
Yeah. I don't know. I think for mathematician, it's very important to control the feeling, mentality. Don't you think so, Trivedi-san? Because if you work hard, then you concentrate, and then if it's successful, then it's okay. But it's not successful. You are, how to say, you stopped somewhere, and you cannot find any other way. Then it was very hard time. So in that case, switch your mind, do other things, and control your feeling normally, then you can do and you can find the right way. So the most important thing is to control the feeling, emotion. So in order to do it, the good thing is to try to smile. So it may be strange, but I think it's true, because if you smile, then the how to say, it's a kind of feedback. If you make a smile here, then the brain understand that I'm happy, misunderstand that I'm happy. So it makes a good circulation.
Yeah, that feeling of positivity is
Positivity.
kind of, yeah, the positivity remains with you.
Yeah.
It
I
helps
think
you
so.
to do whatever you want to do.
Yeah. Always try to be positive. If you are completely, how to say, depressed, even in that case, make a smile on your face, then it will help. I believe it. Then if you
It's
make
a very
smile,
nice advice.
then around the people thought that I'm happy, then they treat me like this, that I'm a happy person. Then it encouraged me. Yeah, so.
That's very nice. It's nicely put. Yeah.
That's a very good piece of advice for anybody, not just mathematicians.
Right. Yeah. There is somebody, someone has left a comment here. Priya Rathod. Ishii, can you see the comment on a chat box?
Chat box? Oh, okay.
Some,
Thank you so much for your nice presentation. Yeah. Oh, okay. Thank you very much. Okay, thank you.
So, if someone else wants to say something,
I'd just like to thank Ishii on behalf of IWM.
Thank you.
Just sorry, I was off and on in between. We thank you profusely for this talk and also the interaction.
Thank you very much.
Thanks a lot.
Thank you very much.
There is a message on the chat box from Riddhi also. Riddhi, what happened? You can't talk? What happened? Hello, Riddhi.
I'm attending the meeting as well as the talk, so it's difficult to talk here, but okay. It was a very nice talk, but I couldn't attend all of it. And
we have the YouTube links. So.
Yes, I'm going to go to the YouTube and attend the whole thing again. So, but I could hear some parts and see it was wonderful. Thank you very much.
Okay, thank you very much.
Vijayalakshmi, you are mute.
So, Riddhi Shah, the person just now who spoke, this person Riddhi Shah, she used to be in TIFR in my institute. But she has to leave because of two-body problem. So, so her husband has a job in Delhi, so she has moved to Delhi herself now. So,
actually, one correction: my husband had a job in Allahabad, and I had a job in Bombay, and then we moved to Delhi, where we got a job together in one city. But we were not together for many years. So we were married in 1991 and we moved in 2007 when my son actually, who used to stay with me, was 12 years old. And we had visited Japan on sabbatical I was in Keio University,
Oh,
and he was visiting Tokyo University under this JSPS
oh, wow.
fellowship. So we used to do that. Sometime we would go for visits to one place so that we can spend time together as a family. But it was very hard. He works in theoretical physics. So especially for my child, it was much harder, and for me to manage him alone for many years. Though TFR has good facilities and all, but those days there was no daycare initially and all, it was much harder. So. And I just want to add, I studied in my own mother tongue, and yeah, it took quite a while to shift. So school, I was in what is called Gujarati, my language. I studied there till 12th standard, 12th grade. And then I shifted to college, and first year I had a lot of trouble. Later maths is okay in English also, but still I had trouble in first year. And when I was giving an interview in TFR, I could not remember the word prime because of the language barrier. Then I had to give them a definition of what it is. So a number which is not divisible by anything other than itself and 1. So then they said, okay, it is called a prime number.
So what is it called going Gujarati?
It's called avibhajya, which comes from
Okay, Sanskrit.
Divided, right.
Yeah, so language sometimes gets lost on us. But I have also heard this theory that if you learn in your mother tongue, then your basic knowledge is better. I don't know how good this theory is, but I have also heard, as Padmavati mentioned, that you learn in your mother tongue, then you learn better as a small young child or whatever. So it's good to see you, and the talk was wonderful. Thank you very much.
Oh, thank you.
But I still have to see the whole talk and interaction. It's only parts of it.
Maybe I should finish the sharing the screen.
Yes, you can stop sharing.
Yeah, stop. Okay, I can see all people.
Neela, why are you wearing mask?
I'm in the office.
In the office, you have to wear mask?
Because it's the staff who's sitting. So.
Okay. So
someone wanted to know what time it is in Tokyo now.
Now it's 9:12.
I think it's too late.
Thanks for your time.
I am a little bit hungry because I didn't eat.
Okay. Yeah. So it was really nice talk actually.
Thank you very much.
Thanks for joining. I mean, this is.
Thank you very much.
Hope you can visit us soon sometime. Hope you can visit us soon, I was saying.
In India.
Hope you can visit us soon.
Yeah, I'd like to come back because I have ever in Kolkata.
Kolkata. Now it's called Kolkata,
Yeah, but not in Bombay or other city. So I'd like to come back. Yeah. After the pandemic.
Keiichi has come few times now, so.
Yes. Yeah, he told me and he enjoyed it very much.
I don't know how I thought he'll be very shocked to see the crowd and thing, but he brought his wife Maiko also here. And
wow, good.
Yeah, they stayed here, so.
Yeah.
So it was really nice having you.
Yeah, thank you very much for inviting me and organize such a nice conference. And chattering with you, very exciting and wonderful. Thank you very much.
Yeah.
Thank you.
Thank you.
Bye.
Okay.
Goodbye.
Yeah.
Thank you. Bye-bye.
See you. See you after pandemic.